Okay, welcome everyone back to the E3SM Coupled Biogeochemistry webinar. This month we have Anand Gnanadesikhan presenting from Johns Hopkins, and Anand is going to be presenting on some of his work related to biogeochemistry. For those folks who do not know Anand, Anand's a physical ocean modeler, but also does a lot of work on the biogeochemical side of ocean modeling and understanding ocean processes. And this talk is focused on the interaction between the physical transport in the ocean and the biogeochemical processes in the ocean. So I think it's got a lot of cross-cutting interest in the project. So with that, I'll hand it I'm going to hand it over to Anand. Please keep yourself on mute and mute your video if you haven't already done so. And I'll hand it over to Anand to start the presentation.
Great. Thank you, Susanna. Thank you for the invitation, and thank you all for showing up. This is work that I've been doing here at Johns Hopkins over the last, almost a decade now with the help of Maria Pradal, Ryan Abernathy, and Alexis Ball. And so the basic problem that we've been interested in is the following. If you look at the ocean, hopefully this video will show, do you see a globe changing color?
Yeah, that looks great.
And so what we see is that this ocean is full of turbulent eddies, and we start off with a zonal pattern of dye, and over time the eddies mix the dye, right? And so the question is, how do we represent that? If we have very, very high resolution models, as E3SM we hope will become, we get a direct representation of this mixing, assuming that all of the physics are accurate. But in a 1-degree model, we have to parameterize all of these flows. And so the question is, then as we parameterize those flows, how do we do that parameterization? Turns out that eddies do two separate things. So if you look at the diagram on the left here, you see eddies having an advective effect. So one of the things that eddies in the ocean do is if you have tilted isopycnal surfaces, they tend to flatten those surfaces, and that generates an advective flow that, in this case, would go counterclockwise, moving light water on the upper right towards the upper left, and dense water in the lower left towards the lower right. So this flattens isopycnals and removes energy, and this is often treated in terms of an interface height diffusion, sometimes called the Jent-McWilliams diffusion coefficient, as shown in the equation at the bottom. But in addition to this advective flow, the eddies also stir flow along isopycnal surfaces. That's shown on the upper right, where you see the arrows are double-headed and that they flow parallel to the sloping isopycnal surface. And this is usually represented as an ansatz, as diffusive ansatz, where the flux is proportional to the gradient along the isopycnal surface or horizontally within the mixed layer times a diffusion coefficient. And it's this diffusion coefficient that we're going to focus on. Because it turns out that while there is a generally agreed upon theory for, let me go back, for the Jent-McWilliams coefficient, which relates it to the slope of the isopycnal surfaces and is based on theories of how unstable waves develop that go back to the 1950s. There is not a good theory for what sets the ready diffusion coefficient. And so as a result, it tends to get used as a tuning knob in a lot of models, and different models use different representations. For example, in the last round of the IPCC, the HAD-GEM model had a value of 500 meters squared per second. For this coefficient, the GFD-LESM had a value of 600, and the CMCC model had a value of 2,000. That's a factor of 4 difference right there. The Max Planck Institute model had the coefficient depend on the grid spacing, with the maximum value being 400. So the average in that model was more like 200, so now we have an order of magnitude range. And then there were a number of models that had the coefficient equal to the Ghent-McWilliams coefficient. The Ghent-McWilliams coefficient generally has a form as shown in the lower left. I've used these two plots to have the same color scale. So the lower left shows a Ghent-McWilliams coefficient, generally topping out at around 1,000 to maybe 1,500 meters squared per second. You can see that the regions that are higher, they're difficult to see because there's not a lot of color contrast there, basically correspond to boundary currents. So Ghent-McWilliams is high, the Ghent-McWilliams coefficient is high in regions where there's sloping isopycnals and is generally topping out at about 1,400 meters squared per second. However, there are alternative parameterizations. The NCAR-CESM is shown on the lower right, and you can see that it generally has a value near the surface of about 2,000. If you go down to 700 meters, it looks very much like the model on the left. So now we're looking at values over much of the ocean in the interior of 200 if you take one parameterization, or 2,000 if you take another. And there are, of course, direct measurements of mixing, but they tend to give very different values than any of the theoretical parameterizations. And this is what, in a paper in 2015, I termed the isopycnal mixing paradox. The paradox arises because the theory suggests that there are low values in the gyre interiors and tropics where slopes are low, and that these values then are, these low values occur in places where the energy is low. However, direct observations suggest that there should be high values in the gyre interior and tropics, and the lower right panel, or the right-hand panel, shows an estimate of diffusion that was basically made by taking the simulation of Ryan Abernathy's that I just showed you, looking at how that simulation affected the tracer that I just showed you, and inverting a diffusion coefficient from that. The diffusion coefficients that you get from this are very, very large. They have a very different pattern than the one on the left. In fact, the correlation with the pattern on the left is pretty close to zero. And if we actually focus in on this, is that you can see on the panels on the bottom, the scale is nonlinear. It goes from 0 to 1,000 in the blues, and then goes up by 1,000 up to 11,000 in the reds. The Ghent-McWilliams coefficient is shown on the left, and you can see how that's high in this region with strong currents, which are shown by the vectors. The Reddy coefficient that Ryan's method produces is actually somewhat offset from that. It has values of around 1 to 2,000 in the core of the Kuroshio, actually maximized just off the axis of the Kuroshio. And so what we did in my group over the last, as I say, this is 7 or 8 years, we've taken a single climate model and we've run it with different representations of this mixing coefficient. So we take constant values ranging from 400 to 2,400, which more or less spans the range seen in the CMIP5 models. And we also take this spatially varying value that I showed you, both show you a close-up of it on this page, but also in the last slide on the lower right. And we take the average version of that model, or of that parameter. So as to see whether it's really important to get the two-dimensional structure, or whether the zonely average structure is really what is contributing to any changes that we see. And so I'm going to show you 3 examples of how this affects biogeochemical cycling. So maybe I can stop and ask if there's any clarifications that people would like to see or hear. Hearing no objections, I'll continue. Okay. So maybe I should just say a little bit more about the climate model that we're using. This is a coarse resolution version of the GFDL ESM2M model. It's a very coarse resolution version. It's about 3 degrees. Unlike E3SM, I can run it on 45 processors and get a year in less than an hour. This means that I can do 1,000-year simulations with many, many tracers. We have about 80 tracers in the model in all. And I run it with a biogeochemistry scheme, which is called the Biology, Light, Iron, Nutrients, and Gases scheme, or BLING for short. It's known as BLING because it's cheap, it looks pretty good, and you wouldn't necessarily want to trust it or the people who are selling it, which would be myself and Eric Galbraith. So I'm going to start off with showing you some results that were published in 2015, where we looked at the uptake of anthropogenic carbon dioxide. This is work that was published in GRL in 2015. And to give you a sense of what we're trying to explain here, the left-hand plot, these are from a paper by Thomas Fröhlicher et al. In a Journal of Climate in 2015. The left-hand plot shows the cumulative uptake of carbon dioxide in petagrams of carbon per degree from a number of CMIP-5 models, and the solid blue line shows the model average, the ensemble average, and the black line is an inversion from Sarah Mikolov-Fletcher. And you can see that there's a lot of variability in the uptake across the different models, and particularly a lot of variability in the Southern Ocean. The right-hand side shows the cumulative uptake as a function of latitude. And so again, what we see looking at the right-hand panel, the vertical axis shows cumulative uptake in gigatons of carbon, and the lowest model has an uptake of about 80 gigatons of carbon, and the highest model has an uptake of about 110 gigatons of carbon. And this is in year 1995, and the inversion of Mikolov-Fletcher is on the high side of that. It has a value of about 110, but the intrinsic observational uncertainty in anthropogenic carbon is about from 85 to 120. So it's not good enough necessarily to distinguish between any of these models. Nonetheless, we would like to know why the models differ from each other. So when we take our model suite, and I'm denoting these, anything with an A ready and a number is a constant diffusion coefficient, and then the number shows the diffusion coefficient. Average 2D is the two-dimensional diffusion coefficient, which goes up as high as 11,000 in the jar centers or immediately off the boundary currents, and average zonal is the zonally average version of that. And so what the top plot shows is the historical anthropogenic carbon dioxide uptake, and the lower plot shows the uptake of the integrated uptake, similar to Mikolov-Fletcher, to the plot on the upper left here. And so what you can see is that the anthropogenic flux actually varies. In this case, it varies by about 16% between 104 and 122 gigatons, so about half of the variation that we see in the CMIP model suite. We see that the largest variation is, in fact, in the Southern Ocean, accounting for about 2/3 of the total variation across the different models. So this suggests that variation in this coefficient could account for a significant fraction of the variation across CMIP-5 models, and that it's important to get it right if you want to get anthropogenic carbon dioxide uptake right. We then compared this with integrated assessment models, and many integrated assessment models use a diffusive parameterization for carbon uptake, where the carbon uptake is a function of depth and simply goes as a diffusion coefficient times the second derivative of the concentration. And the solution of this equation gives you a burden that if you double carbon dioxide overnight and let the interior adjust, the burden will go as that initial increase at the surface times a length scale, which goes as the square root of the diffusion coefficient times time. So if we double CO2 overnight for 3 of the different models, the high mixing model with coefficient of 2400 shown on the top, the low mixing model with a coefficient of 400 shown on the bottom in blue, and the 2D distribution shown in red, we see that they all look rather like a single diffusion coefficient, and if in fact we normalize them to their value at 100 and put a square root on top of that, we see that they collapse as shown on the right-hand side. So we can then back out an effective diffusion coefficient from this to see what the effect of changing the diffusion is. And what we find is that as we go from a value of 400 meters squared per second to 2,400 meters squared per second, the effective diffusion goes as from 2.23 to 3.26 centimeters squared per second, much larger than the explicit vertical diffusion in the model, which is 0.15. So we can think of this vertical diffusion then as this effective diffusion as a background effective diffusion plus the A-ready times the slope squared. And it turns out the contribution from the slope squared diffusion coefficient is consistent with about 4% of the ocean being covered with slopes of order 1 in 1,000, with a long isopycnal diffusion then accounting for about 1/3 of the vertical transport. The rest of the vertical transport is accounted for really by gyre circulation, and gyres, in a sense, behave when averaged globally like large diffusive eddies, which is why this technique seems to work. So most of that diffusion is due to the gyre circulation. This suggests that in E3SM, in which this coefficient is set to 0, we would be missing about 1/3 of the uptake of anthropogenic carbon, potentially. So lessons from this, differences in the lateral mixing coefficient can produce differences in CO2 uptake that are similar in magnitude and pattern to what is seen across Earth system models. But this can largely be understood in terms of an effective diffusion coefficient with a relatively small portion of the ocean involved in fluxing this carbon into the interior. Okay, so now I'm going to move on to oxygen. We've seen that for anthropogenic carbon, which is clearly one of the goals of E3SM in terms of prediction, that this is a maybe 20% effect. What about oxygen? Well, it turns out that oxygen actually has a much bigger spread. What we're trying to explain here is the signal that's seen in this figure. This figure shows results from 6 different CMIP-5 models. The upper left-hand panel shows the global mean oxygen in the control. And what you can see is that it varies a lot. The dotted points show the observations. So there's a few of these models that do a decent job in getting the observations right. There's models that grossly overestimate the oxygen. There's models that grossly underestimate the oxygen. The upper right-hand side shows the volume of hypoxic waters as a function of latitude in millions of cubic kilometers per degree. The hypoxia here is defined as waters having a concentration less than 88 micromoles per kilogram. And this is a level at which higher life forms, fish, to some extent squid, stop being able to breathe. The oxygen concentration gets too low, they're excluded from those waters. And what we now see is that, again, we have a very large range in hypoxic volume. The symbols, the black stars, show the distribution of hypoxic volume by latitude. And basically, none of these models do all that well. The best one is maybe the MPI model in terms of shape, which is the green line. ESM2M does okay in terms of volume, but tends to have too much on either side of the equator. So oxygen is not all that well simulated in most of the CMIP-5 models. What happens when we look at the oxygen change? That's the lower left for the subset of CMIP-5, or for a subset of CMIP-5 models in which we had a 1% increase for 70 years, a constant 1% increase for 70 years until the CO2 doubles. You then hold that constant for another 70 years, and then we look at the last decade of those runs. And when we look at the changes in oxygen, we can see again that they are all over the place. There are some models that show relatively small changes in the 2 to 4 micromoles per kilogram range. There's some models that show very large changes in the 7, 8, 9 micromoles per kilogram range. So there's an order 1 variability in ocean deoxygenation across these models. And what's particularly interesting is if we go to the lower right and we look at the change in hypoxic volume. So this is basically, are the ocean dead zones expanding or contracting? And you can see that in some of the models they expand and in some of them they contract. And I particularly want to draw your attention to the red and green curves. If you look at the upper left-hand panel, the red and green curves are two of the ones that are closest to the observations. The red curve goes up, hypoxia expands in the tropics. The green curve goes down, hypoxia contracts in the tropics. The blue curve is similar. So the three models that have the best simulations of oxygen in terms of the zonal mean don't even agree on the sign. So now let's look at our model suite. If we look at the mean oxygen, now we have the CMIP-5 models in the upper left and the model suite in the upper right. And going from top to bottom, black, red, green, dark blue, light blue, and purple, we go from the 400 mixing case in black, 800 in red, 1200 in green, 2400 in dark blue, the 2D mixing in light blue, and the zonally average in magenta. Lots of things that we can say about this, but the first is that our basic model suite isn't that bad when it comes to getting the oxygen distribution compared to CMIP-5 models, almost all of which are much more expensive than ours. So this is actually pretty good. Another thing that's interesting is that the AREDI and Aber2D models do a pretty decent job of getting the oxygen near the minimum. AREDI, Aber2D, and AREDI 800, AREDI 1200, and Aber2D are the ones that are sort of closest to the observations. There's a large spread in the horizontally average oxygen at depth, but this spread in our model suite is significantly smaller at depth, say below 3,000 meters, than in the CMIP-5 suite, but it's pretty similar at the intermediate depths where the oxygen minimum zones are found. The other thing that's sort of interesting here is that our models with a spatially variable mixing coefficient, even though their peak values are much higher than 2,400 meters squared per second, tend to lie in between our low mixing cases and our high mixing cases. So they look like they have an effective mixing of about 1,000 meters squared per second, which is kind of a canonical value for isopiconal mixing coefficients, which may be one reason that models have historically not done that badly at getting this right, even though they have patterns of mixing coefficients that are almost certainly wrong. Okay, so now let's look a little bit more at these models. The biases in CMIP-5 oxygen at 300 meters are shown here. We see that we have quite different patterns of biases. Many of the models have too much oxygen in the Southern Ocean. They tend to have a ring around the North Pacific gyre of oxygen that's too high. A number of them tend to be too low in the tropical Atlantic. If we compare this with our model suite, we see that we have a somewhat different pattern of biases. All of our models tend to have too much oxygen around the edges of the North Pacific subtropical gyre, whether in the subpolar gyre or on the equatorward edge. So that's that ring in the red ring in the North Pacific that you see there. The contours, which you cannot see, are meant to just indicate the observed mean oxygen concentrations. And what this shows is that it's basically the edges, the regions where you're going from oxygenated to deoxygenated, where we see the differences, the biases relative to observations. At 3,000 meters, the CMIP-5 models are again all over the place. The NOR-ESM in the lower right tends to overestimate oxygen concentrations. The IPSL-MR in the middle right column tends to underestimate them. All of the models do tend to have a low bias in the Eastern Pacific And that is something that we also tend to see in our model suite, that many of our models tend to have a low bias at 3,000 meters in the Eastern Pacific. However, one thing that we see is a high bias as we increase the mixing that develops in the Pacific. This points to something that we'll come back to later, which is that as we increase our mixing, we tend to get overturning in the Pacific that ventilates the Northwest Pacific far more than it is in the real world. So when we think about what drives variation in oxygen, we can think of it in the following. Hello? Okay. If we think about, let's just think about having a simple case where we have oxygen in the deep ocean relative to oxygen in the surface ocean. We can, by definition, break that up into the deep oxygen being the surface oxygen minus apparent oxygen utilization. And that apparent oxygen utilization can be written as a stoichiometric ratio between oxygen and phosphorus. Sorry, that should say O to P, not C to P. Apologies. And the difference between the phosphate at depth and the phosphate at the surface, which we'll call the remineralized phosphate. And I see this looks like it's getting cut off here. I apologize for that, but the bars in the lower left show the differences in oxygen across our model suite relative to the A-Ready 400 case. So the A-Ready 400 case tends to be a bit lower than the observations shown in the dark blue bars. And then we see a pattern of change in oxygen where the A-Ready 1200 case has the highest excess oxygen. Sorry, A-Ready 2400 case has the highest excess oxygen. The quote-unquote realistic mixing cases with a 2D distribution of mixing lie between the 2400 case and the 400 case. If we look at how much of this could be due to changes in the temperature, the saturation, which is what sets the oxygen at the surface, we get the middle set of bars. And so we see the same basic pattern, but a much reduced amplitude. If we look at the differences due to remineralized phosphate, we see the right-hand set of bars. And so clearly, the big driver of this is phosphate. The reason that this doesn't all show up as that if we were to add the middle set of bars and the right-hand set of bars, we'd get something that looks bigger than the left-hand set of bars. And the reason for that is that the oxygen doesn't come to perfect equilibrium in convective regions before sinking into the deep ocean. So these two drivers are not fully expressed. Okay, moving on, let's look at hypoxic volume. Again, the left-hand side shows the different CMIP-5 models. The right-hand side shows our model suite. The black line at the top shows A-Ready 400. The blue line at the bottom shows, on the right-hand side, right-hand panel, shows the A-Ready 2400. The realistic mixing cases lie in between the 1200 and 2400 cases. You can see that there's a very large variation in the total volume, the total area under the curve, depending on what you use as your mixing coefficient. We're using 0 in E3SM, which is somewhat disturbing. That suggests that we're going to overestimate the total amount of hypoxia, and that's going to potentially have some fairly serious effects for nitrogen fixation and nitrogen cycling. To say, we see a threefold range in hypoxic volume across our model suite, which is similar to the range that is seen in the CMIP-5 models. Now, if we look at the changes in oxygen and hypoxic volume, so now the top lines show the CMIP-5 models, the bottom show our model suite. We see a little bit less variability in outgassing or ocean deoxygenation across our model suite, but we see one phenomenon on the right-hand side, the changes in hypoxia, that is reminiscent of what we saw in the CMIP-5 models. We see that in our low mixing models, the red and blue lines in the lower right, they show positive values, so hypoxic waters are spreading. The blue and green show a negative tendency, and so the hypoxic models contract, or hypoxic waters contract. Interestingly, though, if we look at global oxygenation, the largest deoxygenation is actually seen in the green and blue models, the high mixing models, the red and black, show less deoxygenation. So there's a decoupling between the total loss of oxygen. Again, if you look at the lower left, you can see that the black line, the low mixing model, lies on the left-hand side. The green line lies on the right-hand side of the point cloud. The average change there is maybe about 4 micromoles per kilogram, whereas the average change in the green model might be more like -8 micromoles per kilogram. And so the model that has the larger decline in oxygen actually also shows a decline in hypoxia. Why is that? We'll come back to that in a minute. So we see that, again, the range in the mixing suite is about half that in the CMIP-5 models. Both models show differences in whether hypoxic sets of models show differences about whether hypoxic models expand or contract in the tropics. The results are not tightly related to oxygen changes, global oxygen changes, either in the CMIP-5 models or in our model suite. Interestingly, the low mixing models in our suite show expansion, while the high mixing models show contraction of hypoxic waters. And the reason for this is the 3D structure of the changes in oxygen and mixing. So what we're looking at here, the colors show whether you have a contraction or expansion of hypoxic waters, and the contours show the changes in oxygen with a 10 micromolar contour. So, for example, if we look at the A-Ready 800 case, the A-Ready 1200 case here, we see that we've got a big decline in oxygen in the north. This is really the North Pacific. We have a big decline in oxygen coming out of the Southern Ocean, but these plumes of low oxygen are fairly deep. And in this model, the oxygen at that depth is well above the hypoxic minimum. In the tropics, in all of these models, we see an increase in oxygen. It's small, and that increase in oxygen corresponds to a reduction in hypoxia. So in the low mixing cases, the much smaller reduction in hypoxia in the deep, this is really mostly the deep Pacific, but there's some in the deep Atlantic as well, pushes waters into the hypoxic domain, and we get an expansion of hypoxic volume. In the high mixing models, the increase of oxygen at mid depths is what wins. And this increase in oxygen has been seen before. I published about it in a paper in 2012. It's also been seen in the NCAR-CESM. And it's also seen across most, not all, but many of the CMIP-5 models. So IPSL here shows an increase in oxygen and decrease in hypoxia. MPI shows an increase in oxygen and decrease in hypoxia. ESM2G shows something similar. NOR-ESM barely shows it, but again, in all of these, there's some hints of increases in oxygen at mid depths. So again, if we can look at our suite and try to understand what's driving the differences, it turns out that the temperature rise is almost identical across all of these models. All of these models basically show the same uptake of heat and therefore should show the same change in solubility oxygen. This means that oxygen utilization has to be invoked to account for all of the model differences. We can think of that oxygen utilization as a consumption rate multiplied by age. So this differences in oxygen utilization could be due to different amounts of productivity or export of organic matter to the deep, or it could be due to different amounts of time for that organic matter to accumulate in the deep and respire oxygen. It turns out that if we look at productivity, so the top plot shows the primary product or the export production across the different models. The symbols are an estimate from 3 satellite products that we published in a paper in 2007 with John Dunn as the senior author. Basically, you can see that the takeaway here is that these lines are not differing by a factor of 2. We have large differences in oxygen utilization in the deep ocean. We do not have large differences in export production. The differences are maybe 10, 20% across our model suite. Larger on a regional basis, but relatively small when we look at the globe as a whole. However, when we contour these versus age, and I recognize that this is going to be difficult for people to see, but what the colors show the change in oxygen and the contours show the change in age. We have an ideal age tracer in this model that's set to 0 at the ocean surface and ages at 1 year per year below that. And basically what I want you to see is that the contours and the colors more or less map on top of each other. They're relatively well correlated. The correlations are shown by the numbers on the lower right of each plot. And at 300 meters, they range between 0.75 and 0.84. So what's happening is that changes in ventilation, and therefore the time over which waters in the interior have a chance to accumulate oxygen, is what's accounting for the differences in oxygen utilization. That's what's accounting for the changes in oxygen. So basically what's happening is, if we look at the North Pacific, what we're seeing is a big decline in oxygen, which corresponds to an increase in age. We don't see such large changes, however, in the A-Ready 2400, middle of the right-hand panel, or right-hand column here. At 2,400 meters, or 3,000 meters, we see very different patterns. So now the 400 and 800 cases shown up here at the top panels look more or less the same in the North Pacific, but the 1,200, 2,400, 2D, and zonal cases all show a decline in the Northwest Pacific. And although you can't see it very clearly, the contours here also show that there's a change in age. If we, this now is showing the 400, 2,400, and 2D cases on the left-hand side, the changes under doubled CO2, and the O2 errors on the right-hand side, the biases in the base case. And what I want you to see here is that these blue locations where the oxygen is going down and the waters are getting older correspond to places which are biased high in the base state. So what's happening there in the Northwest Pacific is shown in this plot. Now I'm showing overturning circulation in the Indo-Pacific basins. So negative is clockwise, negative is counterclockwise, positive is clockwise circulation. The contour interval is every 3 sphere drips. What we see is we increase our mixing coefficient from A-Ready 400 in the upper left to 800 in the upper right. Oops. There we go. To 1,200, to 2,400, to 2D, and 2D and zonal, is that we develop a shallow overturning circulation in the North Pacific that is very, very strong. It gets up to about 20 sphere drips. Under global warming, that shallow circulation gets turned off. So in the 400 case, we don't start off with much of a circulation, but it's still, here we go, it gets turned off. In the 1,200 and 2,400 case, it shallows. You can see that the maximum here lies below the maximum in the overturning. So that's a shallowing, not a shutoff. Something similar happens in the zonal case here. The implications of that are that the stratification and vertical, why is this happening? You can understand this in terms of stratification and vertical exchange. So these panels show the salinity stratification relative to different depths on the horizontal axis. So moving from left to right, we get more stratification and what we expect to be more stability. The vertical axis shows the oxygen concentration at either 300 meters or 2,400 meters. Observations are down here, so none of the models do all that. All of the models tend to overestimate oxygen at 300 meters. Observations are down here for 3,000 meters. The low mixing models do a pretty good job at getting the oxygen right at that depth. And so what you're looking at is the time series of oxygen versus salinity stratification after we double the CO2. What you see in the upper right is that what happens for both the red and the black, which are the A-Ready 800 and A-Ready 400, is that the stratification increases and the oxygen decreases. So in these models, as we go into doubled CO2, we have an enhanced hydrological cycle that creates an enhanced gradient of salt between the subpolar gyre and subtropical gyre, but the mixing is relatively weak and doesn't mix that away, and so it is capable of shutting down any overturning that's there. In the high mixing models, shown up here in the upper left, the lateral mixing is strong enough to basically keep that collapse of the overturning, which basically follows the Stommel theory from 1961, that basically keeps that from happening. At 3,000 meters, however, the picture is different. We start off at 3,000 meters. The red and the black point clouds show that we start off with relatively low oxygen and relatively high salinity stratification. What happens in those models is that in the high mixing models now, is that while the mixing is capable of maintaining convection to intermediate depths under global warming, it can't keep the convection going all the way down to 2,000 meters, 3,000 meters. And so what happens is that you do get stratification relative to 3,000 meters. The surface does become lighter, and as it becomes lighter and the stratification develops, the oxygen at depth falls off. And we can see that this holds both within models and across models, suggesting that there's a common mechanism here. So lessons for oxygen. What are your takeaways here? Changing this A-Ready mixing coefficient changes oxygen by a lot. The reasons for that change, however, are driven by differences in biological utilization, not by the hydrographic differences in temperature. However, those differences in biological utilization are not primarily driven by the biology, but they're driven by circulation and the differences in ventilation. Finally, whether or not we get a change in hypoxia depends on the depth at which convection turns off and whether the resultant plumes of oxygen loss, which emanate from these convective regions at high latitudes, intersect low oxygen zones. In the high mixing cases, the plumes of low oxygen emanating from high latitudes are pretty deep in the ocean where there wasn't much hypoxia to begin with. In the low mixing models, they're actually at the same depth as the locations where there's hypoxia to begin with. And that's also something that we see in, for example, the HAD-GEM model. Okay, so I'm going to move on to the third part of the talk, which is the question of linearity. And this is from two manuscripts that are currently in prep. So I'm just going to do a very short description or a short outline of some of the things that we're finding here. So what you're looking at here is time series of global surface chlorophyll change in the upper left, global surface biomass change in the upper right, global primary productivity change in the lower left, and global export change in the lower right. For the different models, and the different point clouds are the lower set in each case is cases where we've done an instantaneous quadrupling of CO2, which is one of the standard cases as part of the CMIP process. And the upper point cloud is cases where we've done an instantaneous doubling of CO2. And so there's a couple of things that I think are worth noticing here. One is that the relative spread of these point clouds is different for different variables. So you can see, for example, that for surface biomass, they don't overlap. And this suggests that the uncertainty caused by having the wrong model, as it were, is smaller than the uncertainty in scenarios when one thinks about surface biomass. However, when you look at global primary productivity in the lower left, it's not obvious that's true. The point clouds almost touch each other. And so you can see that there are sort of similar orders of magnitude in terms of the uncertainty in global primary productivity that's due to model structure versus scenario uncertainty. We can also see that the extent to which the models are linear is not always clear. So for example, there's no simple relationship between the size of the change and the mixing coefficient. So if we look at which models show the largest change in chlorophyll in the upper left, under quadrupling, it's the green and the red models, which are the 800 and 1200 meters squared per second mixing cases. That's also true for export. But if we go to the top set of plots, the red model shows the largest change under doubling. The green model is much closer to the blue. It doesn't nearly show the same change. So, and the black model, which has the lowest mixing, always seems to lie in the middle. So this is not a linear progression from low mixing to high mixing. We can also see this if we look at zonal averages. So we're looking at the ratio between chlorophyll, zonally averaged chlorophyll in the high CO2 case versus the control case. The dashed lines show quadrupling, the solid lines show doubling. And again, what we see here, for example, for chlorophyll, we see, let me see if I can, there we go. For chlorophyll, we see that the 400 and 1200 cases show a big drop in chlorophyll, up to 50% at some latitudes. But the low mixing and high mixing cases do not show that same drop. Particular carbon shows the same drop. Again, this is for the 4x case. And that there's also a difference between the 4x case and the doubling case. If we look at where the changes in biomass that we see occur, this shows the natural log of the biomass under the quadrupling case over the biomass in the control case. So values close to 0 are more or less the fractional change. As you get up to a value of 1, that's a factor, plus or minus 1 is a factor of E change. And so what we see is that the changes in biomass are located on the edges of the subtropical gyre. Well, it's actually the gyre edges. It's the edges of the high nutrient regions where we see the changes, not the centers. And so what's basically happening here is that as we change CO2, in those cases where convection is nearly at a tipping point in the Northwest Pacific, we see the convection shuts off or slows down. That doesn't have a big impact on the biomass right near the convective region because the nutrients are pretty high there. But as the nutrients spread out over the Pacific, the edges of the high nutrient region contract, and that produces big changes in biomass. So some preliminary lessons is that the spread across models can be similar to the spread across scenarios for certain fields, particularly primary production, that significant nonlinearities appear across models and scenarios, and changes in convective activity show up in terms of changes in biomass at the edge of the subpolar gyre, at edge of the tropical upwelling where nutrients run out sooner. Okay, so looks like we have some time for questions. I'm going to just give you some conclusions here. Takeaway messages are that eddy mixing produces order 1 differences in hypoxic volume, change of hypoxia in global warming, and change in oxygen under global warming. This coefficient, which as I say has been set to 0 in E3SM, really matters if you're interested in ocean deoxygenation or ocean oxygen dynamics in general. It also produces maybe order 20% differences in a carbon dioxide uptake. The differences are dominated by the impact of eddy mixing in convective regions. So having a high mixing in the recirculation zone of the subtropical gyre really doesn't affect the dynamics all that much. which is good because otherwise our models would have been complete garbage. But in general, the mixing coefficients are high in regions where gradients are relatively low. This is not necessarily true for everything, however, and so we should be aware of that fact. The real differences, or the real controls, seem to be the eddy mixing coefficient in convective regions or regions where the isopyxnals are sloping. The final lesson I think from this is that if we take a realistic parameterization that's based on a satellite-based estimates of convection, we don't break the system. We can actually run with a realistic spatial distribution of mixing, but we need to be careful that that mixing coefficient is aligned with the actual convection. And so that's what I have for now. Thank you very much. Thanks for your attention, and I'll take questions.
Great. Thanks a lot, Anand. That was a really interesting talk. I'm going to end the recording now so that we can do questions offline. So thank you very much.